Hello everyone. So I hope that you have gone through all our previous lecture materials which I have uploaded for stochastic processes too. So today we are going to discuss some theories in stochastic processes. It's most of the terminologies, and in stochastic processes 1 also we have discussed some of these terminologies, but with the time constraint we didn't have much time to discuss them clearly. Therefore, I will be discussing some of the terminologies again, since we want those terminologies to use in the upcoming theorems, right? So, if you can remember when we were discussing about the transition diagrams, the Markov chains we discussed, there are some various there are different types of states, right? So we discuss what are those states types and how to identify those states types. So today also I'm going to discuss about this classification of states, right? Just to remind you the things that we have discussed. So if you have a transition diagram, if you have a Markov chain, right, we can say let's say you have two states in your Markov chain as state I and state J. So you can say state J is reachable from state I, right? That is, you can say it if you can reach state J by finite number of steps starting from state I. Right, starting from state I, if you can reach state J by spending or by taking finite number of steps, we say state J is reachable from state I. And then what is a closed subset? So when you take a transition diagram or Markov chain, you have so many states, right? So if you take a subset out of those states, let's say your subset is capital S, right? So if you take a subset from all your state space, that is from all the states, right? This subset is closed. That is, if you cannot go out from this set, once you reach this subset, if you cannot leave that, if you have no other way to go out from this subset, we call that this subset is a closed subset. That is, if you have a state I in this given subset, right, and if you have another state J which is not belonging to this subset, so the probability of reaching state J from I, that is denoted by Pij, if that is equal to 0, we call that this given subset is closed, right? And then if this subset has only one element, right, that is, if you have only one state where when you reach for that particular state you cannot leave that state, you call that state as an absorbing state or absorbing subset, where you have only one state there. And then we know what is the difference between the irreducible and reducible states, right? So if you cannot, like, if you have a closed set, right, closed set which is a combination of states, it is irreducible, right? That is, if you are able to reach all the states within that subset, so that is what you call as irreducible. So when you take a Markov chain is irreducible if that state space is an irreducible one. So in other words, if in your Markov chain, if you can access all the states, like if you have 3 states, if you can access all of them, if everyone is reachable, we call that Markov chain as an irreducible Markov chain. So these things we have discussed, so just to remind you all. So we look at this example. So if you look at the first diagram, you can see you have three states, state 0, state 1 and state 2. So if you look at state 0, you can see if you want to go to state 1, it's possible, right? From 0 to 1 you can go. And if you want to go to state 2, it's also reachable, that you can go to state 1 and then you can go to state 2. So if you take state 1, you can go to state 2, and if you want, you can go to state 0 as well. So if you take state 2, you can go to state 1 and then you can go to state 0. So you can see in this Markov chain, within all the states, all are reachable. So we call that as an irreducible Markov chain. But if you look at this one, the second transition diagram, you can see if you take state 0, you can go to state 1, and from 0 you can go to 2, and from 0 you can go to 3, and from 0 you can go to 4 as well. But if you take state 4, when from 1 you can go to state 4, but once you reach state 4, you can't reach any other states. Right, that is within the states, all the states are not reachable. So we call it as a reducible Markov chain. So you can see the difference between an irreducible and a reducible Markov chain. Right, so where you have an absorbing state here. So this Markov chain is not a irreducible Markov chain. Right, so here you can see when you look at this one, this is a closed, the absorbing state. When you reach this, you can't leave. And if you look at state 2 and 3, again you can see when you reach state 2, you cannot leave. You can't go, you can go only to state, you can go only to state 3. And when you reach state 3, you can go only to state 2, right? So this subset 2 and 3, it's a subset, it's a closed subset. So you have a closed subset there. So this is actually a reducible Markov chain, where you can reduce your Markov chain into some other parts. And then we are going to discuss the transient and recurrent state. So most of the students ask me, what is this transient state? What is the difference between these transient and recurrent states, right? So it's like this. Now, if you have a Markov chain which consists, let's say, n number of states, so we know from a given state, let's say state I, right? So from state I, if we can reach state J, right? We take, there may be so many paths that we can reach state J. For an example, if you look at this irreducible Markov chain, so if I want to reach state 2 from state 0, I can straight away go to state 1, then go to state 2. Or I can just take one step and come back to state 0 again, and then to state 1, then to state 2 again, another step, and come back to state 2. So you can see there are different ways, the different number of steps that you can take in order to reach a given state, right? By giving that you are in a particular state. So in this case, so the time that you have to spend, that would be different. That is depending on the path, on the number of steps that you are taking. So if you take this minimum time that you have to spend to reach a particular state, we call it as the hitting time, right? So when you take, let's say you have state I and you want to come back again to state I. So this hitting time, right, the time that you want to spend, to come back to that state itself, right, we call it as the recurrence time, right? So that is the recurrence time is denoted by TII. That is the first time that the Markov chain returns to state I. So if you take the probability, this probability as Pi, that is the probability that the state will return back to state I, given that it started from I. So this probability we can calculate it from this, because the number of steps are different. So when you calculate this probability actually, so you will get different values. So what we are interested is where if this hitting time, right? If this hitting time is a finite number, if it is less than infinity, with this probability you can replace this by this term, and when you calculate this probability, if this probability is equal to 1, we call that state as a recurrent state, and if this probability is less than 1, we call it as a transient state. Right, so we need to identify the difference, that is, if when you calculate the probability to reach or to come back the Markov chain, or for the Markov chain to return back to state I, given it starts from state I, if this probability is equal to 1, we call that state as a recurrent state, and if this probability is less than 1, we call it as a transient state. Right, so there are some theorems that we can develop using this transient and recurrent states. That is, if you have a Markov chain which consists finite number of states, then then you can at least find one state which is recurrent. Right, if your Markov chain is a finite Markov chain, then you can find at least one recurrent state. And let's say you have two states in your Markov chain, let's say state I and state J, right? So if state I is recurrent, and if you can reach state J from state I, then we can conclude state J as also a recurrent state. And then if you have a set, let's say S, which is a finite closed irreducible set, and then every state in this set is recurrent, right? And then you have the positive and null recurrent states. Now when you take, now we know when you take this time, the time is different, because depending on the number of steps that you are going to spend to, depending on the path that you are going to take to come back to the same state. So the time is different. So in that case, we can talk about the mean time, right? So the mean recurrence time for state I is denoted by this. So we know that is the expected value of TII. Since the TII is depending on the number of steps that you are going to take, so we can calculate the mean recurrence time using this equation, right? So in this case, when you calculate the mean recurrence time, if that is less than infinity, we call that is a positive recurrent state, and if it is equal to infinity, then we call it as a null recurrent state. Right, and then again we need to know the connections between this positive recurrent and null recurrent. So if you have two states in your Markov chain, let's say state I and state J, and if state J is reachable from state I, and if state I is positive recurrent, then you can conclude state J as also a positive recurrent one. So in earlier case, if state J is reachable from state I, if I is recurrent, J is recurrent. So same thing, if I is positive recurrent, J is also positive recurrent. And then again, if you have a closed irreducible set of states, right? So then every state in this subset is positive recurrent, or every state is null recurrent, or every state is transient. That is, all the states belongs to same category, right? If it is a closed set. And then if S is a finite closed irreducible set, right? In this one, in the previous one, it's not a finite one. So here it is a finite closed irreducible set of states. Then every state in this subset is positive recurrent, right? So actually we can identify these things. Now if you look at this example, okay, so if you look at these examples, what we can do is, now if you look at state 0, if you look at state 0, from state 0 you can reach state 1, and you can reach state 2, and you can reach state 3, and also you can reach state 4. That is, from given that you're starting from state 0, you can reach any other given state. And if you look at state 1, you can reach state 0, you can reach state 2, you can reach state 3, you can reach state 4, right? So all the states are reachable. Let's take state 2, right? If you take state 2, only state 3 is reachable. If you take state 3, only state 2 is reachable. If you take state 4, none of the states are reachable. It's an absorbing state. So when you take your transition diagram, you have to first identify what are the states, right, which can reach all the other states. Those states are known as the transient state. So in this particular Markov diagram, Markov chain, only we can find state 0 and state 1 as the states which can reach all the other given states. So 0 and 1 are transient states. So all the other states are recurrent states, right? All the other states are recurrent states. States 2, state 3, state 4, all these 3 are recurrent states. But here, now if you look at this one, 2 and 3, that is a finite closed irreducible set here. So if you can find a finite closed irreducible set, we call from this theorem in the previous one, see, if S is a finite closed irreducible set of states, then every state in S is positive recurrent. So you can just name these two as positive recurrent states. But state 4 we can't say it since it's an absorbing one, right? So it's a recurrent state. These two are positive recurrent states. So when you are given with the transition diagram, you can identify or you can classify the states with, it's very important when it comes to the theorems that we are going to discuss in the upcoming sessions. Okay. So when it comes to the stochastic process characterization, we know when you take a stochastic process, it's a random variable. When you take t as a time at a fixed time interval, xt1, if you take xt1, that's the random variable observation at that time point. So it's a random variable. So we are going to observe these random variable x at different time intervals, right? So if you take this random variable xt1, right, that is at time point t1, what is the position of your Markov chain? So that is whether you are in state 1, state 0, or whatever the state you are. So that is a random variable. So if you just take the distribution function of that, let's say we want to talk about fxt1, x1, that is the probability where your random variable xt1 less than or equal to simple x1. So if you consider about the joint distribution, so the random variables are xt1, xt2, xtk, and we are interested about the joint distributions where xt1 is less than or equal to simple x1, xt2 is less than or equal to simple x2, likewise, right? So in this case, now you can see we have an observation which is depending with the time. So if we look at the states xt, right, with the time, sometimes we can record time with as a discrete type 1, and sometimes we can record it as a continuous type 1. And if you look at the state space 1, so it also can be discrete and continuous, right? So depending on these two characteristics, we can take a stochastic process and we can categorize our stochastic process into 4 parts, right? 4 parts. So one is sometimes we have discrete time stochastic chain, and sometimes we have continuous time stochastic chain, right? Or sometimes we have discrete time and continuous state process, and sometimes we have continuous time and continuous state process, right? So we'll see with an example. I will explain you the differences between these. So we are going to use this queuing system. So we know, if you like, just imagine that you are going to a supermarket or you are going to a bank, right? So especially these days, so if you want to go to the supermarket, you have to go to the supermarket whatever the time that is possible, and then you have to wait in a queue, right? And then let's say once you collect your goods, you have to go to the cashier, and then you need to stay there for some time to get done with your service, right? And then only you have to leave the system. So the same thing, same scenario is happening at a bank as well. So if you take a supermarket or a bank, if you consider about the customers, now customers are coming at different times. Now let's say the first customer is coming at 9 o'clock in the morning. Let's say the second customer is coming at 9:15. So when you take the difference between the time points that customers have arrived to this supermarket or to this bank, so as for my example, it's 15 minutes. So this time duration, the inter-arrival time, it's depending on how customers are coming. So it's always changing. So it's a random variable, right? So let's take the distribution function of that as F5, that is the inter-arrival time. And then the customers are arriving at different times. Then they have to wait in a queue, and then they have to get done with their service. So the service time also different. So in a supermarket, if you consider as the service time as the time you have to spend in the cashier. So if you have bought so many goods, you have to spend lot of time there, right? So same at the bank. So it's also depending on your requirement. So it's changing. It's a random variable. So let's say take the service time distribution function as Fs, right? So the inter-arrival times, as I told you, if you take the first customer's inter-arrival time as y1, second one's y2, so it has a common distribution. Same with the service times, right? These are independent and identically distributed random variables. So if you take, if you think that in this system, if you have m number of servers, that is m number of cashiers or n number of tellers if it is in a bank. So to describe these distributions, we have different types or methods, right? We have something called the memoryless method, or we have the deterministic method, we have the k-stage method. Likewise, we have different methods. So here when it comes to the stochastic processes, we are considering the memoryless method where we have only one server. That is, we are assuming if you are going to a bank, you are coming at different time points, and then you have to wait in a queue. So to get done with your job, you have only one teller at the bank, so you have to spend there at the service time, right? So we call this as MM1, that is the memoryless inter-arrival service times with the single server. So if you consider about this scenario, right, where you have only one server, now in this case, so we are talking about the classification of the stochastic processes, whether the time is discrete or the state space is discrete or continuous. So if you take the number of jobs waiting in the system at the time of kth job's departure, that is, for an example, let's say when the 6th customer is leaving the bank, or when the 6th customer is leaving the supermarket, how many number of customers are waiting in the queue? There may be 0 customers, there may be 10 customers, so that's a random variable. So if you take the number of customers who are waiting in the system as nk, that is always a discrete number. We can't say there are 10.5 customers in the queue, right? So it's a discrete case. And when we are talking about the departure of the kth one, so that is also a discrete one, right? The 6th customer, 5th customer. So in this case, the state space and the time both are discrete, right? So if you look at this one, the random variable is the number of jobs in the system at time k, right? So that is, if you take at 10:30, how many customers are there, right? So the number of jobs that you have at a particular time, job number is a discrete. You can't say there you have 5.5 number of jobs. So that is discrete. But the time when you take, you can talk about time as a whole number or a decimal, right? You can talk, you can count the number of jobs at 10 o'clock in the morning and maybe 12:30 p.m. So time is a continuous one. So in this case, time is continuous, but you have a discrete state space, right? And if you look at this example, so if you take the waiting time for kth job, that is, if you take the 4th customer, what is the waiting time of the 4th customer? So if you consider about the waiting time can be 30 minutes, 20 minutes, 18.5 minutes. So that can be recorded as a continuous variable. But if you are exactly talking about the kth customer, that is again a discrete one. So in this case, right, you have a discrete time but continuous state stochastic process. And then if you take yt as the total service time for all jobs in the system at time t, right? That is, now for an example, by 11 o'clock in the morning, if you take this teller, this total service time that, or the total time that this teller has been worked by 11 o'clock in the morning is the total service time. So the total service time, since it's a summation of times, it can be continuous. And the time point that we are talking about, it can be 11 o'clock, 11:30, 11:15, then again that is continuous. So in this case, you have a continuous state space and time is also continuous. So there you have continuous time and continuous space. So you can see, depending on your problem, we can identify whether your stochastic process is having a discrete time or discrete continuous continuous time, or discrete or continuous state space. So this is actually very important. Now when it comes to our stochastic process, right, now let's say we are interested about this when you take the distribution function, right, where so you have two variables where we think about the time and we think about the state space. So if you have only one time variable, one variable for time and one variable for state space, we call it as the first order distribution. And if you have two x's, two time values, we call it as the second order distribution. So likewise, if you have n number of time points and n number of x values, so that we call as nth order distribution. So the thing is, now when it comes to the nth order distribution, we can actually further simplify this distribution. So when you take this nth order distribution, we can rewrite this as this probability function, right? So actually, if you can remember, now when we are doing the probability generating functions also, when you have a multiplication, we know how to simplify that. So when it comes to a Markov process, we know if we are interested about the probability where our random variable xt is less than or equal to a given value simple x, given that when at the time point xtn it's equal to xn, xtn minus 1 it's equal to xn minus 1. So since it's a Markov process, we don't consider about the previous values, we are only consider about the current state. So this probability is equal to it's only depending on xtn equal to xn. So that is the characteristic of the Markov chain. So here what we are going to do is we are only dealing with the discrete state Markov chains, right? So here now when you take a Markov chain, sometimes again we can classify these Markov chains as homogeneous and non-homogeneous Markov chains. So most of the times we are dealing with non-homogeneous Markov chain. So if it is a homogeneous Markov chain, what happens is there is sometimes we can identify patterns, right? Similar patterns. Like now for an example, if you take the probability where xt is less than or equal to x, given that xtn is equal to xn. So if you subtract tn from your variable, this will become probability x. T minus Tn less than or equal to x, given that when you subtract Tn from Tn, that is x0 given 0. So these two are having the identical values if it is a homogeneous one, right? So when it comes to homogeneous one, so we know when it is a Markov chain, we always predict the future values by depending on the current values, right? Determining the current value. So when it comes to a non-homogeneous case, the current, if it is a non-homogeneous case, current time can also determine the future, but for the homogeneous Markov chains, current time is also not needed to determine the future. If it is a homogeneous one, we don't even consider about the previous case to determine the future, right? Now in this case, what we are coming to is, now when you take these Markov chains, if you take a continuous Markov chain, now if you take this queuing system, right, you had a waiting time at the queue, you have a service time. So if you take the time you spent in a given state in a homogeneous continuous Markov chain, right, as y, this for this y we can actually talk about y's distribution function, right, the waiting time separately. So which is known as the waiting time of this Markov process, where you have a homogeneous continuous Markov chain, right? So let's see how we are going to find out the distribution and how to do the calculations in these homogeneous continuous Markov chains using this time, the waiting time, that is the time that you spent in a given state. Okay, so I think I'm going to stop from this point. So in the next session, we'll be discussing how we are going to talk about how we are going to use its distribution for the calculations, right? Thank you.